All right, so in this section, we're going to take a look at what is called U substitution. And so the question is, what is it? So we have found that you evaluate an integral by finding the antiderivative. However, this becomes more difficult if the function we are integrating is the result of using the chain rule. And so a situation where the chain rule would have been used, where you had an inside part, that's where U substitution is going to come into play. And what the U substitution does, it's a way of undoing the chain rule so that we can find the antiderivative. So U substitution can also take a more complicated integral and turn it into an easier integral to evaluate. So what you want to do is, first of all, look at your definition of your U substitution over here. The integral of f of g of x times g prime of x dx is equal to the integral of f of u du. All right, so with U substitution, what we need to determine is what is this u value going to be. The u value is going to be the inside function that you would use. And so what we're going to need is the inside of our function to be the u value. However, over here, what we need to also have is the derivative of that u value. All right, so let's take a look at this first example here. With this example, the inside function is going to be this part right here that is raised to the fourth power. So that's what we're going to let u represent, is the x squared plus 9. Now, we are integrating with respect to x, so technically what we would say is we are finding du dx is equal to 2x. Now what we're going to do is we're going to take that dx part to the other side, which now leaves us with du is equal to 2x dx. And so all the time, really, we are going to skip this step right here, and we're just going to go straight to this step and say the derivative of u, we'll call that du, and over here, the derivative with respect to x is dx over on this side. So that the du part right here is going to get replaced with this 2x dx. All right, so let's rearrange some things before we go any further with our integral. This integral is also equal to the integral of x squared plus 9 raised to the fourth power times x dx. Now, we have not changed anything. This integral is the same thing as this integral. All that I've done is taken this x and move it over here next to the dx. So these two integrals are equivalent right here. Now, remember that u is equal to x squared plus 9. So the x squared plus 9, we can replace this with u. That's why we call it U substitution. So what we're going to end up with here is going to be u raised to the fourth power. Now, over here, we need to have du. Now remember, du is 2x dx. All we have is x dx. So what we need then is to insert a 2 into this problem. That will give us du right there. Now, you cannot just insert numbers randomly into problems, because that changes the integral, changes the value of that function. However, if I do something that will undo that 2, then it's okay. What I mean by that is if I put a 1/2 right here, this would undo this 2 because there's all multiplication right here. A half times 2 is just 1, and so 1 does not change the value of this function in here. All right, so now, since I put the 1/2 right there, I can rewrite this problem as 1/2 times the integral of u raised to the 4th power, and this is now the same thing as this, so I can replace that with du. Now the antiderivative of u to the 4th is then u raised to the 5th over 5. That gets multiplied by half from out front, and I can replace that u value with what u was equal to turn this back into an x problem. All right, so that's going to give us then x squared plus 9 raised to the 5th power over 10 plus c. All right, so let's look at the next problem here. In this situation, if you think about chain rule, this would be the inside part, so that's what we're going to let u represent. U is going to be that 3x, which means du is going to equal 3 dx. All right, so if we integrate this or change what this looks like, then this would be sine of 3x, and then we have times dx. Now we want to convert this to u's, so this would be sine of u. However, this needs to be du right here. Du is 3 dx. So we need to insert a 3 right here. Now we can do that, but then we have to counteract what we just did by putting a 1/3 out in front. That undoes that 3. So now we can rewrite this problem as 1/3 times the integral of sine of u, and this is now du, and the antiderivative of sine is negative cosine of u. Oops, no plus c on this. This is a definite integral. And I can replace the u with the 3x. And we are evaluating this between pi over 4 and 3 pi over 4. Now, notice that I did not put my boundaries on my integral right here, because this integral, I turned it into u's, and you got to remember that these two values right here, pi over 4 and 3 pi over 4, those represent x values. Once my integral is written in terms of u, I cannot put x values right here. I would have to put u values. All right, so what we do is we just leave them off until we replace the u with our x's, and now we can evaluate this thing. So this will give you negative 1/3 cosine of 3 times 3 pi over 4 minus negative 1/3 cosine 3 times pi over 4. All right, so this gives us negative 1/3 times the cosine of 9 pi over 4 plus 1/3 cosine of 3 pi over 4. Cosine of 9 pi over 4 is root 2 over 2. So this would be negative root 2 over 3 root 2. And the cosine of 3 pi over 4 is negative root 2 over 2. So this would be let me correct something here. This is not a square root down here. This is a 6. And this would be minus root 2 over 6. And negative root 2 over 6 minus root 2 over 6 gives us negative 2 root 2 over 6, which is negative root 2 over 3. All right, so on this one, we're going to let the u value be our denominator, 4x plus 5, because if we can replace that with a u, that would give us the integral of 1 over u, which is natural log. All right, so we're going to let u be 4x plus 5, which means du is 4 dx. All right, so what that means is that we need to insert a 4 next to this dx. All right, so let me just rewrite this. It's going to give us the integral of 1 over 4x plus 5. I'm going to insert a 4 next to this dx, which means I need to put a 1/4 out in front. We can now rewrite this integral as 1/4 integral of 1 over u du, which is equal to 1/4 natural log absolute value of u, which is 1/4 natural log of 4x plus 5 plus c. All right, so if you look at this one for a second and try to determine what your u value is, remember that whatever you pick for the u value, you want du to be part of your equation. And so if you let u be x squared, you would need to have 2x dx in this problem. Well, we don't have 2x dx, we don't even have x dx. All right, so that's not going to be a good choice. What we want is the exponent right here to be our u value. So we want u to be 2x cubed, because du would be 6x squared dx. Well, we already have the x squared dx. All we need to do is put a 6 in there. All right. So what that's going to give us then is integral from 0 to 1, e raised to the 2x cubed times x squared dx. We're going to insert a 6, which means put a 1/6 out in front. Now, notice that all the problems that we have been inserting things, we've been inserting numbers. Numbers are the only things that you can insert and undo out here. You cannot do this with variables or expressions. You cannot, for example, insert an x right here and put a 1 over x out here. That is not going to give you the same result. You can only do this with constants. All right, so integrating or replacing this with the u's, we're going to get e to the u du, and the antiderivative of e to the u is e to the u. Which, replacing the u with 2x cubed and evaluating this between 0 and 1, that is going to give us 1/6 e raised to the second power minus 1/6 e to the 0 power, which is e squared over 6 minus 1 over 6, or it could also be written as e squared minus 1 over 6. Now, one of the things I want to also show you is that what I mentioned earlier about putting our limits of integration on here. Now, these represent x values, and I left them off once I converted this to a u problem. We could convert our x values to u values as well and continue our integration. For example, let me show you what I mean here. If we have 1/6 integral e to the u du, let's go back to our lower limit right here. This 0 represents an x value. Well, if you come back over here to this equation, when x is 0, that means our u value is going to equal 2 times 0 cubed, which is still 0. So I can put a 0 in here. Now let's do the 1. When x is 1, u would equal 2 times 1 cubed, which is 2. So if I integrate this problem, converting those to u values, we should get the same result. All right, so this would be 1/6 e to the u evaluated between 0 and 2. Well, put the 2 in, and that's going to give you 1/6 e squared minus 1/6 e to the 0, which is the same result that we had earlier. Okay, so we can put different values on here as long as we use our u equation to convert the x boundaries to u boundaries. All right, so this is a little bit different problem here. One of the things you need to try to do is recognize this as an antiderivative. And if you remember, the antiderivative of 1 over 1 plus x squared is tangent inverse. Well, this, if you think of this as integral of 1 over 1 plus this, that would be a tangent inverse problem. So we want the u value to be the inside part, which is 2x, which means du would be 2 dx. All right, so that means we're going to insert a 2 right here, putting a 1/2 out front. That now makes this 1/2 integral 1 over 1 plus u squared du. And the antiderivative of this is our tangent inverse. So this would be 1/2 tangent inverse of u, which would be 1/2 tangent inverse of 2x plus c. All right, next problem we want to take a look at is this one. If you think about what's in the parentheses, parentheses are often a giveaway for what the u value is going to be. Not always, but very often what's in the parentheses will be your u value. So if we try this, let's think about u being that 3x to the 1/2 plus 2. Du then would be 3/2 x to the negative 1/2 dx, which would be the same thing as 3/2 times 1 over the square root of x dx. Well, this part is in the problem already. We can rewrite this as times 1 over square root of x dx. So we see that part in the problem. All we need to do is insert a 3/2, which means put the reciprocal of that out front. All right, so we now can rewrite this in terms of u, be 2/3 integral of u squared, and this is all du. You see how we went from a complicated long integral down to something that's very simple and easy to do. All right, so this is going to give you 2/3 u to the third over 3, which would be 2 times the u value, which was 3x to the 1/2 plus 2 raised to the third power over 3 times 3, which is 9, plus the c. All right, now this one is a little bit more difficult to think about because we don't see parentheses, and parentheses are often what you look for the u value. We also don't see exponents like we did with the e, and so we can't just use the exponent for the u value. So what you want to do is think about, well, we either got natural log of x or x. And x, well, there's just really not much to it. The derivative of x is dx, and we already have dx in the problem. And so that's not really going to help us any. So if we let u be natural log of x, then du would equal 1 over x dx. Well, we can rewrite this problem then as natural log of x times 1 over x dx. This is your u value. I'm sorry, du from over here. All right, so this can be written now as u du, which is equal to u squared over 2. Replace the u value with natural log of x. And that is your antiderivative. All right, so on this one, whenever you see square root of 1 minus something in your denominator, very often you want to think about sine inverse. All right, so for sine inverse, let's try to convert this problem then. I'm going to put the x next to the dx out here and rewrite this as 1 minus x squared squared. So now we can see this as a sine inverse problem. You have 1 over 1 minus u squared. And that would be our sine inverse. So we want the u value then to be x squared, which means du would be 2x dx. Well, we already have the x dx part, so all we need to do is insert a 2 in here, which puts a 1/2 out front, giving you 1/2 integral of 1 over square root 1 minus u squared du, which is 1/2 sine inverse of u, and replacing the u value gives us the antiderivative. All right, so the next problem, again, we don't see parentheses, so that doesn't jump out as our u value. The only exponent we see is a 2. That doesn't jump out as a u value. And so let's think about something else here. Okay, so if you let u be sine of x, and we're going to do this one because the sine of x is raised to a power. All right, so remember that we can think about this as sine of x squared cosine of x dx. So you see the parentheses a little bit better in this situation. All right, so that means du would be cosine x dx. Well, we see that part right here. So this becomes the integral of u squared du, which is u cubed over 3, which would make this sine cubed x over 3 plus c. And our last problem here. If you notice, we have two things that we would typically look for. We have parentheses, and we also have an exponent right here. Okay, so if you let u be just 5x, if u is just 5x, that's still going to leave cosine in the problem, as well as e in your denominator, and that's not going to help us a whole lot. So what I'm going to do is let u be sine of 5x, because du would then be 5 cosine 5x dx. Well, rewriting this problem, this becomes e to the sine of 5x times cosine 5x dx. All we need to do is insert a 5 right here to give us du. All right, so let's go ahead and do that. We'll put a 5 here, which means a 1/5 out in front. All right, so that gives us 1/5 integral 1 over e to the u times, let's see, du. All right, so we got a much easier problem to work with here. Now, 1 over e to the u, we really want to convert to e to the negative u. All right, well, we're going to have another u substitution situation here, except I don't want to use u. Remember that u substitution is, the u value is really an arbitrary letter that we use. It doesn't have to be called u substitution. It could be called t substitution or r substitution or whatever letter you want to use. It's just substitution, really. And so what I'm going to do is I'm just going to let t be the exponent negative u. which means dt would equal negative du. Well, that means I need to insert a negative right here so that I can convert this to a dt. All right, so if I insert a negative here, that means I need to put a negative out in front as well. All right, so this becomes negative 1/5 integral e to the t dt. Well, that is equal to negative 1/5 e to the t. Well, let's replace the t value. T was equal to negative u. All right, so that gives us e to the negative u. But u was also equal to sine of 5x. So what we end up with then is going to be negative 1/5 e raised to the negative sine of 5x plus c.